11th International Physics Olympiad, year 1979, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F. 1996. Problem number 1. A space rocket with mass m equal 12 tons is moving around the Moon along the circular orbit at the height of h equal 100 kilometers. The engine is activated for a short time to pass at the lunar landing orbit. The velocity of the ejected gases u equal 10⁴ meters per second. The Moon radius rm equal 1.7 multiplied by 10⁻³ kilometers. The acceleration of gravity near the Moon surface gm equal 1.7 meters per second square. First question. What amount of fuel should be spent so that when activating the braking engine at point A of the trajectory, the rocket would land on the Moon at point B, figure 1. Question 2. In the second scenario of landing at point A, the rocket is given an impulse directed toward the center of the Moon. To put the rocket to the orbit meeting the Moon surface at point C, figure 2. What amount of fuel is needed in this case? Solution for problem number 1. First question. During the rocket moving along the circular orbit, its centripetal acceleration is created by Moon gravity force. So it means that we have this first equation from which we can find v square. That will be after using expressions for acceleration on the Moon surface. We have v square equal g r square over r plus h. After calculations we can find that this speed on initial Moon orbit we have v equal 1652 meters per second. The rocket velocity will remain perpendicular to the radius vector OA after the braking engine sends tangential momentum to the rocket. See figure 1. The rocket should then move along the elliptical trajectory with the focus in the Moon's center. Denoting the rocket velocity at point A and the point B as VA and VB, we can write the equations for energy and momentum conservation as follows. Now we can use a second equation to express VB through VA and put it to the first equation, and we will get this one. So we can use it to find what is VA square. It will be this one. Taking expression for V in account, we can find velocity change at point A like this. Now we can find the velocity difference subtracting from V, VA, and we will get 24 meters per second. Since the engine switched on for a short time, the momentum conservation law in the system rocket fuel can be written in the form of m minus delta m multiplied by delta v equal delta m multiplied by u, where delta m is the burnt fuel mass. And now along that delta v much less than u, we will find that delta m equal approximately 29 kilogram. That was solution for question A. Solution for question 2. In the second case, the vector is directed perpendicular to initial vector. Thus we have these two expressions for the vector VA. Based on the energy conservation law in this case and from the momentum conservation, the equations can be written in the form of these two equations. Also, we can use formula from previous question 1, that V square equal G multiplied by R square over R plus H. Solving these two equations, again using initially expression for Vc through V, we can rewrite them in form of this one, and using expression from V square, putting here, we finally get that delta V square equal G over R plus H multiplied by H square. And from here we can find what is delta V. That will be 97 meters per second. After that we can do the same manipulation. Using the momentum conservation law, we obtain that delta M now equal 115 kilogram. The only thing I have to emphasize that there are no guarantee that point of land will be in point C, means 90 degrees from initial position, because this lowest position for this ellipsis could be in any other point. So that was a solution for question number 2 and for the full problem number 1. 11th International Physics Olympiad, year 1979, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F. 1996. Problem number 2. Brass weights are used to weigh an aluminum-made sample on an analytic balance. The weighting is once in dry air and another time in humid air, with the water vapor pressure pH equal 2 multiplied by 10 power 3 Pascal. The total atmospheric pressure P equals 10 power 5 Pascal. And the temperature is 20 degrees Celsius, are the same in both cases. What should the mass of the sample be to be able to tell the difference in the balance reading, provided the sensitivity is M0 equals 0.1 milligram. Aluminium density ρ1 equals 2700 kilogram per cubic meter. Brass density is 8500 kilogram per cubic meter. Solution for problem number 2. A sample and the weight are affected by the Archimedes buoyancy force of either dry or humid air in the first and the second cases, respectively. The difference in the volumes between the aluminum sample and the brass weights can be found from the equation delta V equal mass over ρ1 minus mass over ρ2, which is this expression. In that case, mass difference can be found from the ideal gas equation of state in dry air and in humid air. In dry air, we have delta MA equal P delta V multiplied by MA over RT, where MA is a molar mass of dry air, and for humid air we have delta MH equal P delta V MH over RT, where delta MH equal P delta V MH over RT, where MH is molar mass of humid air. Also MV is molar mass of regular vapor. So in humid air, its molar mass is equal to this expression due to proportionality. Finally, to get the difference greater than m0, which is 0.1 milligram, m0 must be greater or equal to delta ma minus delta mh. And after calculations, we have this expression. Or we can rewrite it in form of total mass m must be greater than this expression, and after calculations we will get 0.0439 kilogram or 43.9 gram. That was solution for problem number 2. 11th International Physics Olympiad year 1979 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F 1996. Problem number 3. During the Soviet-French experiment on the optical location of the Moon, the light pulse of a ruby laser, lambda equal 0.69 micrometer, was directed to the Moon's surface by the telescope with the diameter of the mirror d equal 2.6 meters. The reflector on the Moon's surface reflected the light backward as an ideal mirror with the diameter d equal 20 centimeters. The reflected light was then collected by the same telescope and focused at the photodetector. Question 1. What must the accuracy to direct the telescope optical axis be in this experiment? Question number 2. What part of emitted laser energy can be detected after reflection on the Moon if we neglect the light losses in the Earth's atmosphere? Question number 3. Can we see a reflected light pulse with the naked eye if the energy of single laser pulse E equal 1 joule and the threshold sensitivity of eye is n equal 100 light quantum? Question number 4. Suppose the Moon's surface reflects alpha equal 10% of the incident light in the spatial angle 2 pi steradian. Estimate the advantage of using a reflector. The distance from the Earth to the Moon is 380,000 kilometers. The diameter of a pupil of the eye is d equal 5 millimeters. Planck constant is h equal 6.6 multiplied by 10 power negative 34 joule by second. Solution for problem number 3. Question 1. What must the accuracy to direct the telescope optical axis be in this experiment? Solution. The angular resolution of the optical system is estimated by the aperture diameter and the wavelength of light. By the Rayleigh criterion, 2-point sources are considered resolvable when the main diffraction maximum of the airy disk of one image coincides with the first minimum of the airy disk of the other image. If the distance is greater, the 2 points are well resolved, and if less, they are considered unresolved. Rayleigh established this criterion for sources of the same intensity. Taking in account diffraction through a circular aperture, the expression for the limiting angular resolution is written as delta phi approximately equal 1.2 22 lambda over d, where lambda is wavelength and d is diameter of telescope. But since we use a fairly rough evaluation criteria, we can approximately assume that delta phi equal approximately lambda over d, and thus the beam divergence angle delta phi caused by diffraction determines the accuracy of setting the optical axis of the telescope. So we have delta phi approximately equal lambda over d, or about 2.6 multiplied by 10 power negative 7 radians, or approximately 0.05 seconds. Solution for question 2. What part of emitted laser energy can be detected after reflection on the Moon if we neglect the light losses in the Earth's atmosphere? Solution. The part K1 of the light energy of a laser directed to a reflector may be found by the ratio of the area S1 refractor versus the area S2 of the light spot on the Moon, where S2 equal pi r square and r equal L multiplied by delta phi, where L is distance to the Moon. So we have first coefficient K1 equal S1 over S2, or this expression. The reflected light beam diverges as well and forms a light spot with the radius big R on the Earth's surface. And again we have big R equal lambda multiplied by L over D, as small r much less than big R. That's why the part K2 of the reflected energy which got into the telescope makes K2 equal big D square over 4 big R square, which is this expression. And the part K0 of the laser energy that got into the telescope after having been reflected by the refractor on the Moon equals to K0 equal K1 multiplied by K2, or approximately 10 power negative 12. That was solution for question number 2. Question number 3. Can we see a reflected light pulse with the naked eye if the energy of the single laser pulse E equal 1 joule and the threshold sensitivity of eye is equal about 100 light quantum? Solution. The pupil of a naked eye receives as less part of the light flux compared to the telescope as the area of the pupil as E is less than the area of the telescope mirror as T. So we have Ki equal K0 multiplied by Si over S telescope, which is about 3.8 multiplied by 10 power negative 18. So the number of photons big N getting into the pupil of the eye is equal to total energy E, which is 1 joule over energy of 1 photon multiplied by Ke, which is about 12. So the number of photons N getting into the pupil of the eye, since big N less than small n, one cannot perceive the reflected pulse with the naked eye. Question number 4. Suppose the Moon's surface reflects alpha equal 10% of the incident light and the spatial angle 2 pi steradians. Estimate the advantage of using a reflector. Solution. In the absence of a reflector, alpha equal 10% of the laser energy that got into the Moon dispersed by the lunar surface within a solid angle θ1 equal 2 pi steradians. the solid angle in which one can see the telescope mirror from the moon constitutes omega 2 equal S telescope over L square, which is pi d square over 4 L square. That is why the part K of the energy gets into the telescope, and it is equal to omega 2 over omega 1, which is about 0.5 multiplied by 10 power negative 18. Thus, the gain beta, which is obtained through the use of the refractor, is equal to K0 over K, which is 2 multiplied by 10 power 6. That was solution for the question 4, and that was full solution for problem number 3.